Good day and welcome back for part 3 of our discussion on the fundamental theorem of calculus. In this video we are going to focus in on the second part of the fundamental theorem of calculus, which allows us to quickly and efficiently evaluate definite integrals. So as long as we have a function which is continuous, then the definite integral from a to b of the function f of x can be written as big F of b minus big F of a, where big F is any antiderivative of little f. And just a quick reminder from our previous discussions, this is telling us that big F prime is equal to little f. And in terms of notation, we oftentimes will write this big F of b minus big F of a as simply being the function big F of x with a vertical bar next to it, subscript it with an a and superscript it with a b. This is telling us to plug in that upper limit to get f of b, put a minus sign, substitute in that lower limit a. So for a definite integral, as long as this function little f is continuous on the interval from a to b, and we can find any antiderivative, this function big F, we can quickly and efficiently evaluate that definite integral. So a question you might have is, why is this true? And it turns out that it goes back to the first part of the fundamental theorem of calculus. And because I can explain this to you rather quickly and efficiently, I always think it's worth kind of seeing this idea, because this is a fundamental result we will use over and over again throughout our calculus experience. So why is this true? If we remember back to the first part of the fundamental theorem of calculus, we're told that the function defined to be the definite integral from a to x of f of t satisfies that g prime of x is equal to f of x. This is that case where it's the easiest possible function we could imagine differentiating. We simply substitute that x in for t. So this is the fundamental theorem of calculus, part 1. And the reason I write this down is g of x is an antiderivative of little f. So note g of x is an antiderivative of f of x. So let's suppose that we have another one. So if big F of x is any other antiderivative, something that we've seen previously is that if you have two antiderivatives of a function, their relationship is that they are equal up to adding a constant. So f of x would be equal to g of x plus c. And that was something we stated previously in our discussion on antiderivatives, and it followed by the mean value theorem. And don't worry, we're almost done. This is going to give us exactly what we want. What we would like to see is that f of b minus f of a, this quantity on the right, is equal to this definite integral. So let's just go ahead and substitute in and see what we get. So f of b, if we substitute into g of x plus c, is equal to g of b plus c, and subtracting away f of a would be g of a plus c. So c minus c. Also note how these functions are defined. We can substitute in to g of x above. So g of b is the definite integral from a to b of f of t, and we're subtracting away g of a, which is the definite integral from a to a of f of t. And if we integrate any function from a to a, we get back 0. So as desired, this is equal to the definite integral from a to b of f of t. So if we put these two parts together, this gives us precisely the desired result. The definite integral from a to b, and now I'm going to write this as f of x dx. This independent variable t, the symbol we use to represent it, is irrelevant. So I'll call it x to make it look like our formula above. And this is equal to f of b minus f of a, where big F is any antiderivative of little f. So not anything I will ask you to recreate, but once again, since this is such an important property that we use over and over again, I think it's well worth getting some intuition or idea as to where it comes from. And now for the fun part. Let's go ahead and apply this to several examples. So as long as we can anti-differentiate the given function, we should be able to apply the fundamental theorem of calculus. So to get started, let me just remind you of our common anti-differentiation formulas we introduced in our previous section. And these are formulas that we should make sure that we are familiar with, not necessarily things we need to memorize, but we will use these enough that you will know them. You will be able to quickly and easily recall them and use them as necessary. So note, secant of x, and hence secant squared, is continuous on the interval from 0 to pi over 4, so we have no issues whatsoever with applying the fundamental theorem of calculus. And an antiderivative of secant squared is tangent. So applying the fundamental theorem of calculus, the definite integral from 0 to pi over 4 of secant squared x is equal to an antiderivative of secant squared. Tangent of x certainly is 1. Evaluate it from 0 to pi over 4. That is to say, we substitute in pi over 4, we put a minus sign, we substitute in 0. Where we can look above and see that this tangent of pi over 4 minus tangent of 0 is that f of b minus big F of a quantity. But remember, when it comes to trig functions and common values, we should always make sure to evaluate them. So you must take this at least one step further and write 1 is tangent pi over 4, 0 is the tangent of 0, which is of course simply 1. So as claimed, when we can use this fundamental theorem of calculus, definite integrals can become quick and efficient to evaluate. But note the key step. We need to be able to find this antiderivative. That is, somehow our integrand function needs to possibly be manipulated or rewritten so that you can get it to this table of common antiderivatives. That's really all we have to work with at this current moment. So how can we algebraically rewrite to get into the form where we can use this first common antiderivative? Yeah, and hopefully what you're saying is let's break this up into two separate fractions. We can write this as x squared over x plus 2x cubed over x. We can always break a fraction up over addition or subtraction in the numerator. Now we simplify algebraically. So all we're doing is simplifying the integrand. We have not done any calculus yet. We are simply rewriting the integrand algebraically so that it is simpler and easier for us to handle. And note, just like any of these key problems we've encountered this semester, limits, derivatives, now integrals, we need to use good, proper mathematical notation. So at each step along the way, we're writing equal signs, we're aligning things vertically in a single column, we're putting a dx, and these are all things that are necessary and need to be included. If they are missing, you will most likely be missing a few corresponding points. Now we're in a key position. As long as we can anti-differentiate this integrand, we'll be good to go. So note, x plus 2x squared is continuous from 1 to 2, so we can apply the fundamental theorem of calculus. And we're going to use this first common anti-differentiation formula. For that first part x, we're thinking n is equal to 1. In the second part, we're thinking n is equal to 2. So when n is equal to 1, the antiderivative is 1/2 x squared. Then we have 2 times the antiderivative of x squared, which is 1 over 3 x cubed. And by the fundamental theorem of calculus, we evaluate this from 1 to 2. So as claimed when we were talking about antiderivatives, they become a smaller part of a larger problem, as we've illustrated here. We want to make sure that we are quick and efficient when it comes to determining or finding these antiderivatives. Now we substitute in x equals 2. So each x gets replaced with a 2. And then we subtract away what we get when we substitute in x equals 1. And just remember, 1 squared and 1 cubed are also 1. So this would be 1/2 plus 2/3. And the thing I'm going to note is that we most definitely could do some arithmetic and simplify further. But as far as I'm concerned at this point, when we're using the fundamental theorem of calculus, once you get it down to this point where you have substituted the quantities in, as long as they're not things involving, say, common values of trig functions, you are more than welcome to just leave it in this form. And we're going to finish up with one more example of using the fundamental theorem of calculus to evaluate a definite integral. I would like you to pause the video and give yourself, 3 to 4 minutes and see if you can evaluate this definite integral. So hopefully you've paused the video and you've worked through this. Now, the key observation I would like to make is we're not currently in the form where we can anti-differentiate immediately in a single step. So once again, we need to do some algebraic manipulation. But before doing so, I do want to make a small observation to the right. When it comes to differentiating a product, we have a special rule of differentiation. We remember we have the product rule. So when it comes to integrating a product, say we have a function times a function, there is no expectation that we would be able to break this up into two separate integrals. That is to say, I know there might be a temptation to look at this and just say, oh, wouldn't this just be the integral of f times the integral of g? And to be honest, I cringe at really even writing this down. No, there is no expectation or reason why we should be able to break an integral up over a product. So instead, what we need to do is, once again, algebraically manipulate until we get down to terms that we can find antiderivatives of. And here it's a familiar simplification. Just distribute the square root of x through each term, and remind yourself that the square root of x is really x to the 1/2 power, something we've done multiple times in the past. So we have the definite integral from 1 to 3 of 2x to the 1/2 plus, and I'm going to simply write this as x to the minus 5/2. And just so that there's no confusion with the algebra, if you have x to the 1/2 over x cubed, this is x to the 1/2 minus 3, which is why we have x to the minus 5/2 power. Once we get it in this form, we're good to go. We can anti-differentiate each term individually. So for the first term, we're using kind of this opposite of the power rule again, with n equals 1/2. So we would have 2 times 1 over 1/2 plus 1, x to the 1/2 plus 1. And in the second term, we're applying the same formula with n equals minus 5/2. So this would be 1 over minus 5/2 plus 1, x to the minus 5/2 plus 1. And we're evaluating from 1 to 3. So doing a little bit of simplification, we would have 2 times 1 over 3/2, which would be 2/3, x to the 3/2, plus 1 over minus 3/2, x to the minus 3/2. So dividing by 3/2 is multiplying by 2/3. So this becomes minus 2/3 x to the minus 3/2. And now it's a matter of substituting in x equals 3, putting a minus sign, substituting in x equals 1. So 2 times 2/3 is 4/3. and then we substitute in x equals 3. Minus sign, we substitute in x equals 1. And remember, 1 raised to any power is simply 1. So as we've mentioned previously, there's certainly arithmetic that can be done here. But once you get it to the point that you've substituted those quantities in, as long as they're not common values of trig functions, you're good to go. In our next video, I will remind you of both parts of the fundamental theorem of calculus, look at one example of each, and then we'll move on to a class worksheet. Before viewing the next video, I recommend that you go to Canvas, find this associated worksheet, and give yourself a few minutes to complete as much of it as you can. Then we will cover a few of those examples in the video, and full solutions will also be found on Canvas. So stay tuned and take care.